Did anything not obey that rule?
Pitchblende, the uranium ore, is several times more active than the uranium in it can account for.
How do you know that your apparatus isn't flattering you?
Because that is the first thing to suspect, and there is a way to test it.
So how do you go after a substance you cannot see, cannot weigh, and cannot detect by any chemical test?
You use the only thing it does. Dissolve the ore, then perform the ordinary separations any analytical chemist knows.
And the activity tells you which pile to keep.
It tells you where the thing went. If one fraction comes out 10 times more active than the other, whatever we are chasing has followed it, and the rest can go.
You've announced two elements you cannot produce. Why should anyone accept that?
They shouldn't have.
Who breaks the past? Who lights the fire? The minds don't fade, they only rise higher.
I'm Atlas Ingram, and this is Immortal Minds, the show that brings history's greatest minds back for the conversations they never got to have. Becquerel's uranium rays and the two elements that came out of them. Marie Skłodowska Curie, welcome.
Thank you. It is a pleasure to be asked.
Then let's start at the beginning of that road, before any of the work you're known for. Late 1897. Where are you actually working?
A ground floor storeroom at the Municipal School of Industrial Physics and Chemistry.
Which is a trade school.
It is. It trains men for factories, not for the academy.
And the room?
Damp. It was not built for research, and nobody pretended it was. But it was offered to me, and it was enough to begin.
By that point, what have you already done?
License in physics in 1893, ranked first in my cohort. Mathematics the year after, ranked second. One paper published on the magnetism of tempered steels. A commission paid for by an industrial society. And 2 years married.
And a 3-month-old daughter?
Yes, Irene. I keep a book for her as well. Her weight, her teeth, the day each one came. In the same hand I keep the measurements in.
And still no theses for a doctorate?
None. No woman in Europe has completed one in physics, so there is nothing to copy.
Why Paris? You didn't start there.
Warsaw is under Russian rule. Its university does not admit women.
So how did you study at all?
Classes held privately, in apartments, moved when they had to be. We called it the Flying University. It was not a substitute for a laboratory.
And getting out of Warsaw?
6 years as a governess, sending money to my sister Bronia, who was studying medicine in Paris, on the understanding that she would then help me come. And she kept to it.
What is physics doing while you're getting there?
Cracking open. Röntgen announces his X-rays in 1895. Becquerel reports rays from uranium in 1896. Thomson finds his corpuscle in 1897. 3 years, 3 announcements, and the atom is still officially indivisible.
So, late 1897. You need a subject.
Yes, and I need one I can spend years on. X-rays are the fashionable choice, which means they are crowded. A great many capable people are already there. The uranium rays are the opposite. Feeble, and hardly anyone is still working on them.
Quick pause. This conversation never happened. The person on the other side of it died decades ago, and what you're hearing is a dramatization. But we haven't put words in anyone's mouth. Everything they say comes from the record, their letters, their papers, what people actually wrote down at the time. Our team spends hours in that material before a single line gets written. So, yes, the conversation is invented. We'd never pretend otherwise. But what's in it? That's not invented. None of it. If it's been worth your time, the thing that actually helps is following the show, wherever you're listening. That's the whole ask. It's what lets us keep bringing back the people you actually want to hear. And tell us who you want next. We're listening. Now, let's get back to it. Then let's deal with something first. Most people think you discovered radioactivity.
I did not. Henri Becquerel did, in 1896. He left uranium salts in a drawer with a photographic plate wrapped in black paper, and the plate was fogged. Without sunlight, without treatment, without anything being done to it at all. That observation is entirely his.
So what was left for you?
Numbers. He had found something that made a mark. Nobody had found a way to say how much.
And by late 1897, the subject is nearly dead. Why?
Because the effect is weak. It fogs a plate slowly and does nothing dramatic. And Röntgen's rays that same year would light a screen and show you the bones of your own hand. Then papers began appearing, claiming rays from all manner of substances, which nobody could repeat. When a field fills with results that will not reproduce, careful people leave it.
And you walked in.
It was open ground. Very little published to read through, no one ahead of me, no one waiting to publish first.
That took some nerve.
Not really. Had I chosen X-rays, I would have been publishing behind a great many capable people. Here, there was nobody to be behind.
So who was actually paying for this?
Nobody. There were no research grants in the sense you would recognize. Teaching salaries, my husband's at the school, later my own, and the school itself, which gave me the storeroom and did not interfere.
You could live on that?
I had lived on less. In my student years, there was a scholarship, 600 rubles, from the Alexandrovich Fund. When I had earned a little, I took it back to them, so that it could go to another student. As I remember it, they were astonished.
And when you have a result, how does it get out into the world?
Through a member. A communication to the Académie des Sciences must be presented by one of its members, read aloud in the session. Neither of us was a member. Gabriel Lippmann had been my teacher, and he did that service for me. My results went into the room in his voice.
Was there a route to becoming a member yourself?
No, not for a woman. That was the arrangement, and I did not spend time on it.
I want to go back to something. How did you end up in a laboratory with Pierre Curie?
I needed space. I had a commission, the magnetic properties of tempered steels, paid work for an industrial society, and nowhere to do it. A Polish physicist I knew, Józef Kowalski, said there was a laboratory chief at the school who might have a corner free. That is how I met him, over a question of floor space.
Ha! And he was already known for something.
Yes, piezoelectricity, which he had worked out with his brother Jacques, and his work on magnetism. He was 35 and entirely uninterested in advancing himself, which is why he was where he was.
And I guess you guys clicked because you married already in 1895, right?
I would not say clicked, but we understood each other well from the beginning, and it just evolved. So yes, we married in 95 at Sceaux, in July. A civil ceremony, no rings, no white dress. I chose a dark blue one, on the reasoning that afterwards it would be useful in the laboratory. Which it was, for years. The money people gave us we spent on 2 bicycles, and rode them into the countryside for the wedding journey.
I would love to hear more about that, but let's get back to the science. Becquerel had already tried to measure the uranic rays he discovered, but with little success.
He had, with electroscopes, which is the natural thing to reach for, but they are not reliable enough. They drift. You can see that something is happening, you cannot trust the amount.
So what does the effect actually do, physically?
The rays make the air conduct. Ordinarily, a layer of air between 2 metal plates will not pass a current. Put a uranium compound on the lower plate, charge the upper one, and the current crosses. A very small current, but the stronger the source, the larger it is. So the current is the measure.
How small are we talking?
Small enough that reading it directly is hopeless, so we did not read it. We cancelled it.
Explain that.
Pierre and Jacques had built something years before, for quite another purpose. A sliver of quartz, hung so that you can load it with weights. Squeeze or stretch a quartz crystal, and it releases charge on its faces, and the charge is known. Not approximately, exactly, in strict proportion to the force you apply. So you have a source of electricity you can dial, with a hook and a scale pan.
Ah, so you feed one against the other.
Yes, the chamber sends charge one way, the quartz sends it the other, and between them sits an electrometer with a needle. Now, if I try to read the current directly, I am reading a quantity at the very edge of what the instrument can resolve, and I am reading it of a needle that will not sit still. So I do not read it. I keep it at 0. If the two charges are equal, the needle does not move at all, and I add weight to the quartz at exactly the rate that holds it there, with a chronometer running. And when it is finished, I do not have an impression of a stronger or a weaker effect. I have a figure. This much charge in this much time.
That sounds easy to do badly.
Yes, you are onto something. You are loading weights with one hand and holding a chronometer in the other, keeping a needle still that does not wish to be still. And the whole thing answers to damp, to the temperature of the room, to a door closing somewhere.
How long before you could trust yourself with it?
Months. Other laboratories obtained the same apparatus, the same chamber, the same quartz, the same electrometer, and could not reproduce the measurements. The apparatus was not enough on its own. I was, in a real sense, part of the instrument.
So now you can compare. What did you compare?
Everything I could obtain. Uranium metal, its oxides, its salts, its compounds, dry, powdered, dissolved, in the dark, in the light, warm, cold.
And then?
Every other element I could get hold of. Then minerals.
And what did the numbers say?
That the activity of a uranium compound depends on one thing only: how much uranium is in it. Not which compound it is, not whether it had been heated or illuminated, or dissolved, or chemically transformed into something with entirely different properties. Take the uranium apart and put it into something else, and it brings its activity with it, unchanged, in exact proportion to how much of it is there.
What does that mean?
It means the emission is not a chemical event. Chemistry is what atoms do with one another, how they combine, what they release, what they take up. Every one of those things I altered, deliberately and repeatedly. I heated the compounds. I illuminated them. I dissolved them and precipitated them and built them into other substances entirely. And the emission did not respond. Not weaker, not stronger, not delayed. So it does not belong to the compound. The compound can be taken apart and put back together, and the emission does not notice. It belongs to the uranium atom itself, in the way that its weight belongs to it.
And the atom, in 1898, is
Indivisible. That is the word in the textbooks. The thing that does not come apart and has nothing going on inside it. I am not able to tell you where this emission comes from. I can only tell you that nothing I do to the chemistry touches it.
Did anything not obey that rule?
2 minerals. Pitchblende, the uranium ore, is several times more active than the uranium in it can account for. And chalcolite, a copper-uranium mineral, is also too active.
How do you know that your apparatus isn't flattering you?
Because that is the first thing to suspect, and there is a way to test it. Chalcolite has a known recipe, so I made it. Artificial chalcolite, built up in the laboratory from pure ingredients, the same substance by every chemical test. And I measured it.
And?
Exactly what its uranium predicted, not a fraction more. So the excess is not in the formula, and it is not in my instrument. It is in the natural ore.
Then what could do that? You've got a rock more active than everything you know is in it. Reason it out for me.
Start from what pitchblende is. It is largely uranium ore, and the rest of it is substances I had already put through the electrometer, one at a time. Lead, bismuth, copper, silica. Every one of them inactive. Nothing in that list emits anything at all. So what I have in front of me is a quantity of inactive material, plus a quantity of uranium that I have weighed and therefore know exactly. And the whole of it is several times more active than that weight of uranium would be on its own. Something in the ore I have not accounted for. Not more uranium. I weighed the uranium. Something else, far more active than uranium, in a quantity so small that ordinary chemical analysis has walked past it for 100 years.
An element nobody has ever seen, predicted by a needle not sitting still.
By a number. And I would not say predicted.
What would you say?
That everything else had been excluded, it was a conclusion I could not avoid, not a vision.
Before you publish that, you get beaten to something. Tell me about thorium.
I had found that thorium compounds are active as well. Uranium was not alone. And when I came to publish, I learned that Gerhard Schmidt in Germany had published the same thing a few weeks earlier.
A few weeks. That's a hard way to lose something.
It is the ordinary way. Two people at the same open question arrive at the same near thing at nearly the same time. He had thorium. Nobody had the pitchblende anomaly.
And that's it?
I acknowledged him in the note and went to the part that was still mine.
And the note itself, April 1898.
The 12th of April. Rays emitted by the compounds of uranium and thorium, the measurements, the thorium, and at the end, the anomaly. Liebman read it into the session, as he had to.
Your first real claim on the world, and it enters the room in another man's voice.
That was the rule. He read it accurately.
And this is the point Pierre puts his own work down.
Yes.
Just like that?
He had spent years on crystal symmetry and on his own instruments, and he set them aside. For a few months, he thought. He never went back to them. It was his decision, and I did not have to argue for it. There was clearly something in that ore, and two people could get at it faster than one.
So how do you go after a substance you cannot see, cannot weigh, and cannot detect by any chemical test, when the only thing it does is make air conduct?
You use the only thing it does. Dissolve the ore, then perform the ordinary separations any analytical chemist knows. Precipitate this group, dissolve that one, split it into fractions. And measure every fraction.
Aha! And the activity tells you which pile to keep.
It tells you where the thing went. If one fraction comes out 10 times more active than the other, whatever we are chasing has followed it, and the rest can go. Repeat, and it concentrates.
So you're following the substance through the chemistry.
No, we couldn't. It was far too scarce to have any chemistry we could see. We were following its signal.
Nobody had done that before.
Not as a method for finding elements. The radiation had become the instrument.
Okay, so we are in July 1898. What's in the notebook so far?
The activity had settled into a fraction that travels with bismuth. On the 13th of July, there is a symbol in Pierre's hand in the book. PO. 5 days later, the note went in. A new radioactive substance contained in pitchblende, about 400 times more active than uranium.
400 times. And you name it in the same note.
Conditionally. The sentence says, if the existence of this new metal is confirmed, we propose to call it polonium, from the name of the country of origin of one of us.
Is that modesty?
It is not. We had a strongly active fraction that behaved in a particular way. We did not have the metal. Those are different things, and the sentence had to say so.
And the country of origin of one of you did not exist.
Not on any map. Poland had been divided among 3 empires for a century. Warsaw was Russian. So the name went into chemistry instead, where it could not be legislated away.
Anything else in that note that hadn't existed before?
The word radioactive appears there in print for the first time. I needed a term for the property, and there had not been one.
By December, there's a second one.
A second active fraction that would not behave like the first. Polonium travels with bismuth. This one followed barium all the way through and would not be parted from it. Different chemistry, a different substance.
And you're not doing that alone.
No. Gustave Bemeau ran the chemistry instruction at the school, and he worked those separations with us. Barium is a difficult company to keep. The note of the 26th of December carries 3 signatures: Pierre Curie, Marie Curie, and Gustave Bemeau. People remember 2 of those. There were 3.
And you had a witness outside your own instrument.
Which mattered enormously, because we were making a claim on the strength of a measurement we had invented ourselves. Eugène de Marsay was the best spectroscopist in Paris. He examined our concentrates and found a line belonging to no known element. And each time we handed him a more active preparation, that line was stronger. 2 methods, independent of each other, pointing at the same thing.
Now let me make the case against you, because the chemists did. You've announced 2 elements you cannot produce. Why should anyone accept that?
They shouldn't have. I would not have.
Meaning what?
An element is not admitted on a signal. To put a thing into the periodic system, you must hand it over. A weighable quantity of a pure substance, a spectrum, and an atomic weight arrived at by measurement rather than inference. And I want to be clear that I thought that was the right standard. I was not being obstructed. It is precisely what keeps the table from filling up with enthusiasm.
And how much radium is in a kilogram of ore?
We did not know. Very small, parts in a million at best, and in fact far less. Which meant the objection had exactly one answer.
Which was?
Tons. If radium is there in traces, you begin with an enormous quantity of ore, and you reduce it. There was nothing clever to do instead. And we couldn't afford tons of pitchblende. It was mined at St. Joachimsthal in Bohemia, in Austria, for the uranium, for coloring glass. But uranium was what they took out, and radium is not uranium. The radium should still be in the residue they threw away.
So, you asked for the garbage?
That sounds absurd, right? But yes, through Austrian colleagues and the Academy of Sciences in Vienna. About 100 kilograms free of charge to begin with, then tons of it on very favorable terms. It arrived in sacks in the courtyard, and because it had been dumped on slag heaps in the Bohemian forests, it came with pine needles in it.
Pine needles.
The first operation of the discovery of radium was sorting pine needles out of dirt.
Where do you process tons of ore? Not the storeroom.
A shed across the courtyard, given up by the medical faculty as unfit even for dissections. Bituminous floor, glass roof that lets the rain in, no ventilation to speak of. Unbearable in summer. In winter, you worked in your coat. When the furnace fumes became too much, we carried the boiling out into the yard.
Was it as bad as it sounds?
I am not the person to ask. Wilhelm Ostwald came to see where it had been done. He wrote afterwards that it was a cross between a stable and a potato cellar, and that if he had not seen the chemical apparatus, he would have supposed someone was playing a joke on him.
Walk me through what a day of that actually is.
I worked the material in batches of about 20 kilograms. Dissolve, precipitate, filter, wash, concentrate, again. Sometimes a whole day, mixing a boiling mass with an iron rod nearly as large as myself, in a yard, and at the end of it, I would be broken with fatigue. And that is only the crude stage, tons to kilograms. Then the real work, separating radium from barium, when their chlorides are so nearly alike in solubility that it cannot be done in one operation. Crystallize, take the fraction that is slightly richer, dissolve it, crystallize again.
How many times?
Thousands. Each cycle gains you a little, and the next one has to be done exactly as the last, or you give the little back.
And Pierre?
He was measuring. After every stage, so that we knew whether we were gaining or losing. And increasingly, the radiation itself, what the rays were, how they behaved. He wanted to know what the thing was doing. I wanted it in a bottle. It was a very good division.
The picture almost everyone carries is two people alone in a shed. And some of it comes from the way you told it later.
That is fair. When I wrote about those years, 20 years afterwards, I told it as the two of us against the difficulty. Partly because that is how it felt, and partly, I will admit, because I was arguing for laboratories to be funded. Hardship argues better than acknowledgements do.
So who else should be in the picture?
The school, which housed us, paid Pierre and asked nothing. Vienna, without those residues there is no radium at all. Beaumont, de Marseille, and André de Bierne, a young chemist who came to help, and who found a third element of his own in the same residues in 1899, actinium. He stayed with me the whole of my working life.
And that's everyone?
Not quite. Tons to kilograms was eventually contracted out to industrial works with de Bierne supervising. We did not do all of it by hand. We could not have.
What was it doing to you, physically?
Our fingertips cracked and hardened and would not soften again. It is difficult to handle delicate apparatus with hands like that. And we were tired in a way that sleep did not correct.
And him?
Pains in his legs and his back. We attributed them to rheumatism and to working in a damp shed. And then, in 1901, he strapped a radium preparation to his arm and left it there for hours. Then recorded the skin for weeks afterwards, how the wound opened, how slowly it closed. Becquerel had been burned by accident, carrying a tube in his waistcoat pocket. Pierre wanted it done properly and observed.
That's an experiment on himself.
And it was encouraging. If radium destroys diseased tissue as readily as it destroyed his arm, there is a use for it in medicine. Physicians in Paris were treating lesions with it within a year or two.
I'll say this once and then leave it alone. Nobody in that shed had any way of knowing what else the exposure was doing.
No, we knew about the skin.
Was there anything good about that room?
We used to go back into it at night. The preparations were on the shelves and on the tables, and in the dark you could see them, feebly luminous silhouettes all round the room. We would walk about looking at them.
Just looking.
Just looking. I have written that it was in this miserable old shed that we passed the best and happiest years of our life.
After everything you've just told me about it.
Both of those things are true. I am not going to choose between them for you.
So it is the year 1902. What do you finally have?
About a decigram of pure radium chloride. 1/10 of a gram. From tons of residue. And 4 years.
And what does 1/10 of a gram get you?
Everything that was demanded. It could be weighed. It gave a clean spectrum. And it was enough to determine the atomic weight. About 225, which places radium below barium in the periodic system, exactly where its chemistry says it belongs.
Lord Kelvin had been saying publicly that radium might be nothing new at all.
He had, and until 1902, that was a respectable position to hold.
And after?
After 1902, it was not a position anyone could hold. There was a weight, and anyone could go and check it.
The argument is over. What exists in 1903 that didn't exist in 1897?
A word, a method, and two elements, and a property that a substance can emit steadily out of itself regardless of what you do to it chemically. Which means the atom is not the closed, finished thing the textbooks describe. There is something going on inside it.
What did you think was going on inside it?
I did not know. That is the honest answer, and it was the answer in 1903. Pierre and Albert Laborde had just measured something that made it worse. Radium salts give out heat, continuously, without being warmed by anything and without visibly running down. A quantity of heat that does not come from anywhere we could name.
That's a serious problem for physics.
It is a scandal for physics. Energy is not supposed to appear. Rutherford and Soddy in Montreal were proposing that these substances are transforming, that one element is becoming another, which, put plainly, is what the alchemists were accused of believing. I was cautious. It was a serious suggestion from serious men, and it might well be right. But it rested on inference, and I had just spent 4 years learning what inference is worth before somebody puts the substance on a balance. We measured. We did not commit.
Did you accept it?
I was cautious. It was a serious suggestion from serious men, and it might well be right. But it rested on inference, and I had just spent 4 years learning what inference is worth before somebody puts the substance on a balance. We measured. We did not commit.
And then, in June 1903, the Royal Institution puts on a Friday evening discourse on radium. Who gives it?
Pierre, the Friday discourses are their great public occasion, and the custom was that a woman did not speak from that lectern. So the lecture on radium was given by one of us, and I was in the audience.
Who sat beside you?
Lord Kelvin. He crossed the room and took the seat next to mine, in front of everybody, which was noticed. He had been the most prominent doubter about radium, and he was extremely courteous to me personally. Both of those things were sincere.
Okay, now tell me one thing. During research, I found something specific. So tell me about Pierre's hands that week.
Yes, you found correctly. They were very bad. The skin on his fingers had cracked, and it did not close. That spring, he had difficulty dressing himself, and buttons were beyond him some mornings. He gave the lecture anyway, and during the demonstration, he spilled a little of the radium, a small quantity. As I understand it, they never entirely got it out of that room.
6 days later, you're at the Sorbonne.
The 25th of June. Lippmann, Bouty, and Moissin examined me, and the doctorate was awarded très honorable. Later in November, the Royal Society gave us the Davy Medal, the two of us together.
Let me ask about the process itself. You could have patented the isolation method.
We could have. It was put to us directly. By then, there were people who wanted to manufacture radium and would have paid for the right.
How long did it take you to decide?
An afternoon.
That's quick.
Well, if you find something, you publish it completely. The method, the failures, the quantities, so that anyone can repeat it. That is what a physicist does. To hold back the procedure and sell it would have been a different profession.
An industry grew on it.
Within a few years, in Germany and then elsewhere, we had almost nothing from it. I do not regret the decision. I have occasionally regretted the laboratory it would have paid for.
Now, Stockholm and the Nobel Prizes. Walk me through it, because the paperwork is a story on its own. Who was nominated?
For the Physics Prize of 1903, a group of French members of the Académie put forward two names, Becquerel and Pierre Curie.
Who were they? The members?
Darboux, Poincaré, Mascart, and Lippmann, who had read my first note into the Academy himself 5 years earlier.
Your name is not on it. What changes that?
A letter. Gösta Mittag-Leffler, a Swedish mathematician who had taken an interest in the position of women in science, wrote privately to Pierre to tell him what had been submitted. Pierre wrote back on the 6th of August that if he were to be considered, he wished to be considered together with Madame Curie, with respect to our research on radioactive bodies.
That's the whole argument?
He did not argue it at length. He simply declined to be considered alone.
And that was enough, procedurally?
Not by itself. But Charles Bouchard of the Paris Faculty of Medicine had put my name forward the year before, in 1902. So the nomination existed, and Pierre's letter is what made the committee reach for it.
Wait, weren't you already nominated in 1902 by Gaston Darboux and Emile Voorburg?
I was, but I didn't win. And Nobel nominations don't roll over. When the French Academy submitted their official list for 1903, they completely left me off.
So how did you win? The committee can't award a prize to someone nobody nominated.
That is correct. But Charles Bouchard had filed a separate, independent nomination for me for the 1903 prize. Because the deadline was so early, he mailed it in late 1902.
Aha! So the paperwork already existed. Pierre's letter just forced the committee to use it. How was the 1903 prize actually divided then?
Half to Becquerel for the discovery of spontaneous radioactivity. Half between the two of us, jointly, for our research on the radiation phenomena discovered by Professor Becquerel.
Isn't there something missing?
Polonium, radium. Neither word appears. The chemists on the committee took the view that the discovery of elements was a matter for the chemistry prize and should be kept for that. So the physics citation credits the work on the phenomenon and stops there.
So you were given a prize for radiation research, and the two things you spent 4 years extracting from a mountain of Bohemian slag are not mentioned.
That is what the document says. And the chemists were not wrong about their own jurisdiction. It was simply the second time that year that the record left something out.
You didn't go to Stockholm.
We were ill and tired, and Pierre could not tolerate the ceremony. The lecture was required, so it had to wait. Pierre delivered it in June of 1905, and he credited my part in it throughout, which he did not have to do, and which people noticed.
How long did it take for the elements to get their own citation?
Whole 8 years. The chemistry prize in 1911 for the discovery of polonium and radium. The words the 1903 citation would not print.
There's one other thing that happens in 1903, which is that the press arrives, and the picture that forms is two people, alone, in a shed. Where did that picture come from?
From the shed, partly. It was genuinely a bad room, and journalists liked it enormously. It made a better article than a school and a courtyard and a list of colleagues would have. And from us, because we were tired and did not correct much of what was written.
Only partly from you, then.
No, mostly from me, in the end. I was not lying when I wrote about those years. I was leaving things out, which is a thing I would never have permitted myself in a measurement, and permitted myself quite easily in a memoir.
We have a tradition here. Everybody gets 3 questions to finish with. What do people most misunderstand about you?
That I discovered radioactivity. I never claimed it, and it was never true. Becquerel found the phenomenon, and I said so in every paper I wrote.
And under that?
That it was done by 2 people in a bedroom. Beaumont worked the separations and signed the radium paper with us. De Marce found the line in the spectrum that made the claim publishable at all. De Bierne came as a young chemist, found an element of his own in the same residues, and stayed with me for the rest of my working life. The Austrians sent the ore, without which there is nothing to work on at all. And the school gave us the room and asked us for nothing. And secondly, people often think that I was austere. That is nonsense. There was a year after my gymnasium, in the countryside, before Paris, and the letters I wrote in it are mostly about kuligi, carnival sleigh parties. As I remember it, we danced until morning. That is also me.
Second, what did the world gain from your work, and what did it cost?
A phenomenon that can be measured rather than described. A method for finding substances by their radiation. Polonium and radium. A property that belongs to the atom, which means the atom has an inside, whatever turns out to be in there. And all of it published completely, patented by nobody, so that anyone who wanted to repeat it could. Sadly, as you mentioned correctly, there comes a cost with these discoveries. After 4 years of hands-on chemistry, I did not get back the body I began with. My fingers never went right again, and I got tired in ways I was not used to. To add to it, in August of 1903, I lost a child.
I am so sorry. The weight of that must have been unbearable. You wrote a letter to your sister Bronya shortly after it happened. You told her, "I had grown so accustomed to the idea of the child that I am absolutely desperate and cannot be consoled."
Yes. I kept both columns of the price I paid. I have never pretended either one was smaller than it was.
Let me ask the last one. In 1897, you were foreign, unfunded, working in a borrowed storeroom, and you chose the question nobody wanted. Somewhere tonight, there is a young researcher exactly there. No title, no money, no one waiting on her results, holding a question the field has already walked past. Before any of this was proven, before anyone read your name into a room, what did you know then that she needs to hear now?
Find a way to put a number on it. Whatever she is looking at, if she can only describe it, she has an opinion. A number can be set beside another number, taken next week by someone else, and that comparison is the whole machinery. Most of what I did was not thinking. It was learning to measure well enough that the measurement could be trusted. And also I learned a lot about how plants actually go down. We named radium in 8 months. It took 4 years to put 1/10 of a gram of it into anyone's hand. Whatever she is planning for, she should plan for the 4 years and not the 8 months.
4 years, tons of Bohemian mining waste, 1/10 of a gram, and a Nobel citation that could not bring itself to print the words polonium and radium. Marie Skłodowska Curie, thank you.
Thank you. You had done the reading.
This was Immortal Minds. New episode every week. Follow or subscribe wherever you're listening, and you'll get it the moment it lands. Next week, we will be joined by the man Newton told us he stood on, Galileo Galilei, who couldn't time a falling body, so he ran it down a ramp and weighed the water that poured out of a vessel while it fell. I will see you then.